Close your eyes for just a moment and imagine something with me. Imagine you are floating, completely alone, in the vast emptiness between Earth and the Sun. There is nothing around you for millions of miles in every direction. No air, no sound, no wind, no clouds, no ground beneath your feet. Just you, suspended in an infinite black void. Now turn your head slowly and look toward the sun. There it is, blazing with a fury that defies human comprehension. A ball of fire so massive that you could fit 1,300,000 Earths inside it, burning at temperatures that reach 15 million degrees Celsius at its very core. The surface alone rages at 5,500 degrees Celsius, hot enough to vaporize every material known to humanity. It is the most powerful furnace in our entire solar system, an unrelenting nuclear engine that has been burning without pause for 4.5 billion years, pouring energy into the cosmos at a rate of 384.6 septillion watts every single second of every single day. That is not a number your brain can comprehend. That is not a number any human brain can comprehend. It is energy on a scale so vast that if you tried to count the joules released in a single second, you would be counting for longer than the universe has existed. And yet, right here, right where you are floating, just a few million miles from this cosmic inferno, you are freezing. Your body temperature is dropping. The side of you facing away from the sun is plunging toward temperatures colder than anything you have ever experienced on Earth. Colder than the deepest Antarctic winter, colder than liquid nitrogen, approaching 270 degrees below 0 Celsius. That is just a few degrees above the coldest temperature that is physically possible in this universe, a boundary called absolute zero, the point at which all molecular motion ceases, the point at which physics itself says no colder is possible. How is this happening? How can you be so close to the most powerful source of heat in our solar system and yet be freezing to death? How can the sun burn with the fury of 10 billion nuclear bombs every second, and yet the space right next to it remains one of the coldest environments in existence? This is not just a curiosity. This is not just a fun fact for a dinner party. This is one of the most profound questions you can ask about the nature of reality itself, because the answer takes us on a journey through the very foundations of physics, through the birth of quantum mechanics, through the engineering marvels of human space exploration, through the ultimate fate of the entire universe, and most surprisingly of all, through the reason why you and I and every living thing on this planet exist at all. So let us begin this journey together, and I promise you, by the end of it, you will never look at a sunny day the same way again. Before we can answer our central question, we need to confront something that most people never think about. Something so fundamental that it seems almost embarrassingly simple, and yet when you truly understand it, it changes everything. We need to ask ourselves what temperature actually is. Now I know what you are thinking. Temperature is how hot or cold something is. That is what we learnt in school. That is what the thermometer tells us. When you touch a hot stove, the temperature is high. When you grab an ice cube, the temperature is low. Simple, right? Wrong. That understanding, the one that almost every person on Earth carries around in their head, is not just incomplete. It is fundamentally misleading, and it is the very reason why the paradox of cold space seems so confusing in the first place. Here is what temperature actually is, at the deepest level that physics can currently describe. Temperature is a measure of the average kinetic energy of the particles that make up a substance. Let me say that again because it is that important. Temperature is a measure of how fast, on average, the tiny particles, the atoms and molecules that make up any piece of matter, are moving, vibrating, and jostling around. When you heat something up, you are not adding some mysterious substance called heat to it. What you are doing is making its atoms and molecules move faster. When something is hot, its particles are zooming around at incredible speeds, smashing into each other, vibrating with tremendous energy. When something is cold, its particles are barely moving at all, sluggish and slow, huddled together with minimal energy. Think of it this way. Imagine a room full of people. If everyone in the room is running around at top speed, crashing into walls and bouncing off each other, that room has a high temperature. If everyone is standing perfectly still, barely breathing, that room has a low temperature. The temperature is not some separate thing floating around in the room. The temperature is the movement of the people. No people, no temperature. And this, right here, is the key insight that unlocks our entire paradox. Temperature is not a thing that exists on its own. Temperature is a property of matter. It is a description of what matter is doing. If there is no matter, there is nothing to have a temperature. And what is space? Space is the closest thing in the universe to absolute nothingness. It is a vacuum so empty that in the vast stretches between stars, you might find one single lonely atom in every cubic centimetre. Compare that to the air you are breathing right now, which contains roughly 25 quintillion molecules in every cubic centimetre. 25 followed by 18 zeros, 25 million trillion particles in a space smaller than the tip of your finger. Space is emptiness on a scale that makes the most barren desert on Earth look like a crowded shopping mall. So when we say space is cold, what we really mean is not that space has a low temperature in the way that your freezer has a low temperature. What we mean is that there is almost nothing there to have any temperature at all. Space is not cold the way ice is cold. Space is cold the way silence is quiet. It is the absence of the thing, not the presence of its opposite. And this distinction, as subtle as it might seem, is the entire foundation upon which our understanding rests. But we need to go even deeper, because understanding temperature is only half the puzzle. We also need to understand something that most people confuse with temperature all the time, and that is heat. In everyday language, we use heat and temperature almost interchangeably. We say it is hot outside, meaning the temperature is high. We say turn up the heat, meaning make the temperature higher. But in physics, heat and temperature are two very different things, and confusing them is like confusing speed and distance. They are related, but they are not the same. Temperature, as we just discussed, is a measure of the average kinetic energy of particles. It tells you how fast the particles are moving on average. Heat, on the other hand, is the transfer of thermal energy from one object to another. Heat is energy in motion. Heat is what happens when a hot thing gives some of its energy to a cold thing. Temperature is a state. Heat is a process. Here is an analogy that might help. Think of a bathtub full of warm water. The temperature of the water might be, say, 40 degrees Celsius. That is a measure of how fast the water molecules are jiggling around. Now, the total thermal energy in that bathtub is enormous, because there are trillions upon trillions of water molecules, all moving, all carrying energy. Now think of a tiny spark from a sparkler on a holiday celebration. That spark might have a temperature of over 1,000 degrees Celsius, far hotter than your bathwater. But here is the thing. If that spark lands on your skin, it does not burn you. Why? Because even though its temperature is incredibly high, meaning each individual particle is moving extremely fast, there are so few particles that the total amount of thermal energy it carries is minuscule. The bathwater at 40 degrees would warm you up far more than the spark at 1,000 degrees. The bathwater has more heat to give, more thermal energy to transfer, even though its temperature is much lower. Now apply this thinking to space. The particles that do exist in space, those incredibly rare and lonely atoms floating in the void between stars, might actually be moving quite fast. In some regions of space, these sparse particles can have temperatures of thousands or even millions of degrees. But because there are so absurdly few of them, the total thermal energy, the total heat in any given volume of space is essentially zero. You could fly through a cloud of gas at 10,000 degrees Celsius in space and barely feel anything, because even though each particle is moving at tremendous speed, there are so few particles hitting you that the total energy transfer is negligible. This is why the corona of the sun the outermost layer of its atmosphere, has a temperature of 1 to 3 million degrees Celsius, far hotter than the surface, and yet if you could somehow stand in it, you would not be instantly vaporized by its heat. The corona is incredibly hot, but incredibly thin. Its temperature is extreme, but its density is so low that the actual heat it could transfer to you is surprisingly limited. Temperature without density is like speed without mass. A feather moving at 100 miles per hour is not going to hurt you. A truck moving at 10 miles per hour might crush you. Density matters. Matter matters. And in space, there is almost no matter at all. Now let us talk about something that connects all of this together, and that is how heat actually moves from one place to another. In physics, there are 3 and only 3 mechanisms by which thermal energy can be transferred, 3 ways that heat can flow from something hot to something cold. These 3 mechanisms are conduction, convection, and radiation, and understanding each of them is absolutely essential to understanding why space is so cold, despite the sun being so hot. Let us start with conduction. Conduction is the simplest and most intuitive form of heat transfer. It is what happens when you touch a hot pan and your hand gets burned. The fast-moving molecules in the hot pan crash into the slower-moving molecules in your skin, transferring their kinetic energy directly through contact. The heat flows from the hot pan to your cooler hand through a chain of molecular collisions. One molecule bumping the next, which bumps the next, like a line of dominoes. Conduction requires direct physical contact between particles. It requires matter touching other matter. It works best in solids, where molecules are packed tightly together and can efficiently pass energy along the chain. It works less well in liquids, where molecules are farther apart, and even less well in gases, where molecules are widely spaced and collisions are less frequent. Now think about space. In the vacuum of space, there is essentially no matter. There are no molecules packed together. There is no chain of particles to pass energy along. Conduction in space is effectively zero. The sun cannot heat space through conduction because there is nothing to conduct through. Strike 1. Next comes convection. Convection is the transfer of heat through the bulk movement of a fluid, which in physics means either a liquid or a gas. When you boil a pot of water, the water at the bottom gets hot, expands, becomes less dense, and rises. Cooler water from the top sinks down to take its place, gets heated, and rises in turn. This creates a circular current, a convection current, that efficiently distributes heat throughout the pot. Convection is incredibly effective. It is the reason your home heating system works, the reason weather patterns exist, the reason ocean currents circulate heat around the globe. But convection requires a fluid medium to carry the heat. You need moving gas or moving liquid to transport thermal energy from one place to another. And in space, there is no fluid, there is no gas, at least not in any meaningful density. There is no medium through which convection currents can form. The sun cannot heat space through convection because there is nothing to convect. Strike 2. And that leaves us with radiation. Radiation is the odd one out, the rebel of the heat transfer world, because unlike conduction and convection, radiation does not require any medium at all. Radiation is the transfer of energy through electromagnetic waves, through photons, those tiny packets of light and energy that travel through the vacuum of space at the ultimate speed limit of the universe, 299,792 kilometers per second. Every object in the universe that has a temperature above absolute zero emits electromagnetic radiation. Your body is radiating right now, emitting infrared photons that carry your thermal energy out into the environment. A campfire radiates visible light and infrared radiation. The sun radiates across the entire electromagnetic spectrum, from radio waves to gamma rays, with most of its energy concentrated in visible light and infrared. And here is the crucial thing. These electromagnetic waves can travel through the vacuum of space with absolutely no problem. They do not need air, They do not need water. They do not need anything. They are self-propagating disturbances in the electromagnetic field, and they zip through empty space at the speed of light, carrying energy from the sun to Earth and beyond. So the sun is radiating energy into space, enormous, staggering amounts of energy. Every second, the sun emits enough energy to power human civilization for millions of years, and this energy is traveling through the vacuum of space. So why does space not heat up? If the sun is blasting radiation in every direction, and this radiation is traveling through space, why is space still so cold? The answer is deceptively simple and profoundly important. Radiation traveling through empty space is energy in transit. It is not heat until it is absorbed by matter. Think of it this way. Imagine a dark room with a flashlight. You turn on the flashlight and a beam of light shoots across the room. The beam itself does not illuminate the air, not visibly. You cannot see the beam from the side unless there are dust particles in the air to scatter the light. The beam is energy traveling from the flashlight to whatever surface it eventually hits, the wall, the floor, your hand. The air in between is not lit up, not warmed, not affected in any meaningful way. The energy passes through without interacting. Now scale this up to the cosmic level. The sun is the flashlight. Space is the dark, dustless room. And the planets, asteroids, dust clouds, and every other piece of matter out there are the walls and surfaces. The sun's radiation streams through the vacuum of space, traveling for millions and billions of miles, and the space itself is not heated because the radiation does not stop there. It does not interact with the vacuum. It passes through as if the vacuum does not exist. Because in a very real sense, for the purposes of absorbing radiation, the vacuum does not exist. There is nothing there to absorb the energy. There is nothing there to convert the radiation into thermal motion of particles. The photons just keep going, sailing through the emptiness at the speed of light, until they eventually strike something. A planet, a moon, a grain of dust, an astronaut's spacesuit, your face on a sunny day, and only then, only at the moment of absorption, does the radiation become heat. Only when a photon is absorbed by an atom, transferring its energy to that atom and making it vibrate faster, does the process of heating occur. This is the heart of our paradox, and it is so simple that it is almost anticlimactic. Space is cold because the sun's energy passes through it without stopping. The vacuum of space is transparent to radiation. It does not absorb, it does not scatter, it does not interact. It just lets the energy through, like a perfectly clear window letting sunlight into a room. The window itself does not get as hot as the sunlight it transmits. The vacuum of space does not get as hot as the radiation it transmits. The energy is there, streaming through at the speed of light, but it is energy in transit, not energy absorbed, and without absorption there is no heating. But if you think we are done, if you think that simple explanation is the whole story, then you are vastly underestimating how deep this rabbit hole goes. Because now we need to ask a follow-up question that is just as fascinating as the original. If the sun's radiation can travel through space without heating it, then what happens when that radiation does hit something? What determines how hot an object in space gets? Why is Mercury scorching on one side and freezing on the other? Why is Venus hotter than Mercury even though it is farther from the sun? Why is Earth in the perfect sweet spot for life? And what would happen to you if you were floating in space right now? These questions take us into the realm of thermal equilibrium in the vacuum, and the physics is gorgeous. Let us start with the concept of thermal equilibrium in space. Every object in the vacuum of space is engaged in a constant, never-ending balancing act between two processes, absorbing radiation and emitting radiation. These are the only two things an object in space can do thermally, because as we established, conduction and convection are off the table. There is no air to carry heat away, there is no surface to conduct heat into. All an object can do is catch photons and release photons. And the temperature that object settles at its equilibrium temperature is determined by the balance between these two processes. If an object absorbs more radiation than it emits, it heats up. If it emits more than it absorbs, it cools down. When the amount absorbed equals the amount emitted, the temperature stabilizes, and we say the object is in thermal equilibrium. This principle is governed by one of the most beautiful equations in all of physics, the Stefan-Boltzmann law, which states that the total energy radiated by an object per unit time is proportional to the fourth power of its absolute temperature. In mathematical notation, it is P equals sigma times epsilon times A times T to the fourth, where P is the power radiated, sigma is the Stefan-Boltzmann constant, epsilon is the emissivity of the surface, A is the surface area, and T is the temperature in Kelvin. The key insight here is that T to the fourth power. This means that if you double the temperature of an object, it does not radiate twice as much energy. It radiates 16 times as much energy. 2 to the fourth power is 16. This is an incredibly steep relationship, and it means that as an object gets hotter, it becomes dramatically more efficient at radiating energy away. This creates a natural self-regulating system. If an object in space starts absorbing a lot of solar radiation and heating up, its own emission of radiation increases rapidly following that fourth power law until it reaches a temperature where it is emitting exactly as much as it is absorbing. Conversely, if an object is in shadow and not absorbing much radiation, it cools down, and as it cools, it emits less and less, until it reaches the point where its reduced emission matches its reduced absorption. This is why objects in space reach stable temperatures rather than heating up forever or cooling to absolute zero. Now let us do something fascinating. Let us calculate what temperature an object would reach if it were floating in space at the same distance from the Sun as Earth, about 150 million kilometers away. At this distance, the intensity of solar radiation, what scientists call the solar constant, is approximately 1,361 watts per square meter. That means every square meter of surface facing the Sun receives 1,361 watts of radiant energy. For a perfect black body, a theoretical object that absorbs all incoming radiation and emits radiation with maximum efficiency, the equilibrium temperature at Earth's distance from the Sun works out to approximately 279 Kelvin, which is about 6 degrees Celsius. That is surprisingly cold actually, it is above freezing, but barely. It is a chilly day, not the warm and comfortable environment we enjoy on Earth's surface. And this tells us something incredibly important. The raw equilibrium temperature that sunlight alone would produce at Earth's distance is not particularly warm. The reason Earth's average surface temperature is about 15 degrees Celsius rather than 6 degrees Celsius, and the reason some parts of Earth are much warmer than that, is because of our atmosphere. The atmosphere acts as a blanket, trapping some of the outgoing infrared radiation and sending it back down to the surface, creating what we call the greenhouse effect. Without the atmosphere, Earth would be a frozen world. The oceans would be ice. Life as we know it would be impossible. The atmosphere is not just the air we breathe, it is the thermal insulation that makes our planet habitable, and it is a direct consequence of the physics we have been discussing. The atmosphere does what the vacuum of space cannot. It absorbs radiation, it traps heat. It uses all three mechanisms, conduction, convection, and radiation, to distribute thermal energy around the globe, smoothing out the extreme temperature swings that an airless world would experience. And this brings us to one of the most dramatic illustrations of our paradox anywhere in the solar system, and that is the Moon. The Moon is essentially the same distance from the Sun as Earth, give or take a few 100,000 kilometers, so it receives roughly the same intensity of solar radiation. But the Moon has no atmosphere, no air, no greenhouse gases, no thermal blanket. And what happens? The temperature swings are staggering. On the sunlit side of the Moon, where the surface is directly exposed to solar radiation, temperatures can reach 127 degrees Celsius, well above the boiling point of water. But on the dark side, the side facing away from the sun, where the surface is exposed to the void of space with no sunlight to absorb, temperatures plummet to negative 173 degrees Celsius. That is a swing of 300 degrees from one side to the other, on a body that is roughly the same distance from the sun as we are. And at the boundaries between light and shadow, these extreme temperatures can exist just meters apart. You could literally stand with one foot in blistering heat and the other in unimaginable cold. This is the paradox of space made tangible, made visceral, made real on a surface you can almost reach out and touch when you look up at the night sky. The moon is the perfect demonstration that the sun's heat does not spread through space like warmth from a fireplace. It travels in straight lines like arrows of light and only heats what it directly strikes. The space between the sun and the moon, the vacuum through which that radiation travelled, remains cold and empty and untouched. Let us now go on a tour of our solar system, because each planet tells a different version of our story, and the variations are as fascinating as the central theme. Mercury, the closest planet to the Sun, orbits at an average distance of just 58 million kilometers, less than half the distance from the Sun to Earth. You would expect Mercury to be the hottest planet in the solar system, and on its sunlit surface it does get astonishingly hot, reaching temperatures of about 430 degrees Celsius. Hot enough to melt lead, hot enough to melt zinc, hot enough to destroy virtually any human-made object. But here is the twist. On its night side, the side facing away from the sun, Mercury's temperature drops to negative 180 degrees Celsius. That is a temperature range of over 600 degrees, the most extreme of any planet in our solar system. And the reason is the same as the moon. Mercury has virtually no atmosphere. There is no blanket to retain heat, no medium to distribute it, no buffer against the extremes. When the sun shines on Mercury, the surface absorbs radiation and gets blisteringly hot. When the sun sets, the surface radiates its heat away into the void, with nothing to stop it, and the temperature plummets. Mercury rotates very slowly, taking about 59 Earth days to complete one rotation. So the same side faces the sun for weeks on end, getting hotter and hotter, while the other side faces the void for weeks, getting colder and colder. It is a world of fire and ice, separated not by thousands of miles, but by the simple angle of sunlight. Now let us look at Venus, and here is where things get really interesting. Venus is the second planet from the Sun, farther away than Mercury, orbiting at about 108 million kilometers. You would expect Venus to be cooler than Mercury since it is farther from the Sun and receives less solar radiation per square meter. But Venus is the hottest planet in the solar system. Its surface temperature is a staggering 465 degrees Celsius, hotter than the sunlit side of Mercury, and here is the truly remarkable part. This temperature is nearly uniform across the entire planet. Day side, night side, equator, poles, it makes almost no difference. Venus is a furnace everywhere, all the time. How is this possible? How can a planet farther from the Sun be hotter than one closer to it? The answer is the atmosphere, or more specifically, the atmosphere from hell. Venus has an incredibly thick atmosphere, about 90 times the pressure of Earth's atmosphere at its surface, and it is composed of 96% carbon dioxide, one of the most effective greenhouse gases known to physics. This massive blanket of CO2 traps solar radiation with ruthless efficiency. Sunlight enters the atmosphere, is absorbed by the surface, is re-emitted as infrared radiation, and then is trapped and retrapped again by the thick CO2 atmosphere, bouncing back and forth between the surface and the atmosphere in an endless cycle of heating. The result is a runaway greenhouse effect, a positive feedback loop that has turned Venus into the hottest planet in our neighborhood, despite being nearly twice as far from the Sun as Mercury. Venus is the ultimate proof that the temperature of a world is not simply determined by its distance from the Sun. It is determined by how that world handles the energy it receives. Mercury is naked to space, gaining and losing heat with wild abandon. Venus is wrapped in the thickest thermal blanket in the solar system, hoarding every photon of energy that enters its atmosphere. And Earth? Earth is the Goldilocks case, with just enough atmosphere to keep temperatures moderate, just enough greenhouse effect to raise the temperature from a chilly 6 degrees to a comfortable 15 degrees average, but not so much that we tip into a Venusian nightmare. We exist on a razor's edge of atmospheric chemistry, and the physics of radiation and heat transfer are the forces that hold us there. Moving outward from Earth, we encounter Mars, the red planet, a world that tells yet another version of our story. Mars orbits at about 228 million kilometers from the Sun, about 1.5 times the distance of Earth. It receives only about 43% of the solar radiation that Earth receives. And it has an atmosphere, but a pitifully thin one, about 1% the pressure of Earth's atmosphere, mostly carbon dioxide, but simply not enough of it to create a significant greenhouse effect. The result is a cold, harsh world with an average temperature of about -60 degrees Celsius. But even on Mars, the temperature swings are dramatic. Near the equator on a summer day, temperatures can briefly reach 20 degrees Celsius, comfortable enough for a light jacket. But at night, they plunge to -73 degrees or colder. At the poles, temperatures can drop to -140 degrees Celsius. Mars shows us what happens when you have a little atmosphere, but not enough. It smooths out the temperature extremes slightly compared to an airless body like Mercury or the Moon, but it cannot provide the kind of thermal regulation that makes a planet truly habitable. As we continue outward into the solar system, the temperatures keep dropping and the Sun's influence keeps weakening. And this is where the inverse square law becomes dramatically important. The inverse square law states that the intensity of radiation from a point source like the Sun decreases with the square of the distance. If you double your distance from the Sun, you do not receive half the radiation. You receive 1/4. Triple the distance and you receive 1/9. This is because the Sun's energy radiates outward in all directions, spreading over the surface of an ever-expanding sphere. As that sphere gets bigger, the same amount of energy is spread over a much larger area, and any given square meter receives less and less of it. At Jupiter, roughly 5 times farther from the Sun than Earth, the solar intensity drops to about 50 watts per square meter, a mere 3.5% of what Earth receives. Jupiter's cloud top temperature is about -110 degrees Celsius. At Saturn, about 9.5 times Earth's distance, the solar intensity is roughly 15 watts per square meter, and cloud top temperatures are about -178 degrees Celsius. At Uranus, 19 times out, the solar intensity is about 3.7 watts per square meter, and the temperature drops to -224 degrees Celsius, making Uranus the coldest planetary atmosphere in the solar system. At Neptune, 30 times Earth's distance, the solar intensity is just 1.5 watts per square meter, and temperatures are about -214 degrees Celsius. And way out at the edges at Pluto, roughly 40 times Earth's distance, the Sun is so distant that it appears as little more than a very bright star, and temperatures hover around -230 degrees Celsius. But here is something that makes the outer solar system even more interesting. Jupiter and Saturn are actually warmer than they should be based solely on the sunlight they receive. Both of these giant planets have significant internal heat sources. Jupiter radiates about twice as much energy as it receives from the Sun, and Saturn radiates about 2.5 times as much. This internal heat comes from the slow gravitational contraction of these enormous gas giants, a process that converts gravitational potential energy into thermal energy. Jupiter's interior is estimated to be about 24,000 degrees Celsius hotter than the surface of the Sun. So even in the distant cold reaches of the outer solar system, heat still exists. It just comes from a different source, not from the Sun's radiation, but from the planet's own gravitational energy. This reminds us that the sun is not the only source of heat in the universe. Gravity, radioactive decay, tidal forces, and other processes can all generate thermal energy. The universe has many ways to be warm, even in the darkest, most distant places. Now let us go back to the vacuum of space itself and ask an even more profound question. We said that space has almost no matter in it, and therefore the concept of temperature barely applies. But is there any sense at all in which we can assign a temperature to empty space? The answer is yes, and it comes from one of the most important discoveries in the history of cosmology. In 1965, two radio astronomers named Arno Penzias and Robert Wilson were working at Bell Labs in New Jersey with a large horn-shaped antenna originally built for satellite communications. They kept detecting a persistent, low-level microwave noise coming from every direction in the sky, a faint hiss that they could not eliminate no matter how hard they tried. They checked their equipment, they rebuilt connections. They even famously climbed inside the antenna and cleaned out what they diplomatically described as a white dielectric substance, which was in fact pigeon droppings. The noise persisted. They were frustrated and puzzled. They did not realize at the time that they had accidentally stumbled upon one of the most profound discoveries in the history of science. That persistent hiss was the cosmic microwave background radiation, the CMB, the afterglow of the Big Bang itself, the remnant heat from the birth of the universe. Let me explain what the CMB is and why it matters so deeply to our topic. When the universe was very young, about 380,000 years after the Big Bang, it was a hot, dense plasma of subatomic particles and radiation, so hot and so dense that light could not travel freely. Photons were constantly being absorbed and re-emitted by the soup of particles, bouncing around endlessly like a ball in a pinball machine. But as the universe expanded, it cooled, and eventually it cooled enough for atoms to form. A moment called recombination. When atoms formed, the universe suddenly became transparent to light. Photons that had been trapped for hundreds of thousands of years were suddenly free to travel, and they have been traveling ever since, for 13.8 billion years, stretching across the expanding universe, losing energy as space itself stretches, shifting from the hot visible light they started as to the cool microwave radiation they are today. This radiation fills every cubic centimeter of the universe. It comes from every direction. It is the oldest light in the cosmos, and it has a temperature. When we measure the CMB, we find that it corresponds precisely to the radiation that would be emitted by a black body at a temperature of 2.725 Kelvin, which is negative 270.425 degrees Celsius. That is just 2.725 degrees above absolute zero. And this, in a very real sense, is the temperature of the universe. It is the background temperature of empty space. If you could somehow shield an object from every star, every galaxy, every source of radiation in the universe, and leave it floating in the void for long enough, it would eventually cool down to 2.725 Kelvin, matching the temperature of the CMB. It would reach thermal equilibrium with the faint afterglow of creation itself. This is the ultimate cold of space. Not absolute zero, not quite, but very, very close. And it is not an arbitrary number. It is a fossil, a relic, a record of the most violent and creative event in the history of everything, the moment when the universe itself came into being. The discovery of the CMB answered many questions and opened many more. It confirmed the Big Bang theory. It showed us the age of the universe. It revealed the seeds of cosmic structure, tiny fluctuations in temperature that would eventually grow into galaxies and galaxy clusters, and the vast web of cosmic structure we observe today. When we map the CMB across the sky, as satellites like COBE, Doppler map and Planck have done with increasing precision, we see a remarkably uniform glow with tiny variations, fluctuations of about 1 part in 100,000. These fluctuations are like the wrinkles on the face of the newborn universe, and they contain an astonishing wealth of information about the composition, geometry, and fate of the cosmos. But for our purposes, the most important thing about the CMB is what it tells us about the temperature of space. Space is not absolutely cold. It is not at 0 Kelvin. It is bathed in this faint ubiquitous radiation, this cosmic background warmth that keeps it at 2.725 Kelvin. That is the floor. That is the coldest that the vacuum of intergalactic space can naturally get. And even this minuscule temperature, this barely above absolute zero whisper of warmth, is a gift from the Big Bang, a remnant of the unimaginable heat of creation, cooled and stretched over 13.8 billion years of cosmic expansion into the faintest possible glow. There is one place in the universe we know of that is actually colder than the CMB, and it is the Boomerang Nebula, located about 5,000 light-years from Earth in the constellation Centaurus. The Boomerang Nebula is a planetary nebula, a cloud of gas and dust blown off by a dying star. The gas is expanding so rapidly, at about 164 kilometers per second, that it has cooled below the temperature of the CMB, reaching approximately 1 Kelvin, negative 272 degrees Celsius. This makes it the coldest known natural object in the universe. The physics behind this is fascinating. When a gas expands rapidly, it does work on its surroundings, pushing against the outside pressure, and this work costs energy. The gas pays for this work by losing thermal energy, which means its temperature drops. This is the same principle behind how your refrigerator works, and it is the same reason why aerosol cans feel cold when you spray them. In the case of the Boomerang Nebula, the expansion is so violent and so rapid that it has chilled the gas below the cosmic background temperature, but this is a temporary state. Over time, the nebula will absorb CMB photons and slowly warm back up to match the universal background. The Boomerang Nebula is an anomaly, a brief exception to the rule that nothing in nature can be colder than the CMB without active cooling. Now, I want to take a detour that I think you will find absolutely fascinating, because it shows just how intimately connected our paradox is to the deepest physics of the modern era. Our story about why space is cold despite the sun being hot is, at its heart, a story about radiation, about how objects emit and absorb electromagnetic waves, about the relationship between temperature and the kind of radiation an object produces. And it was precisely this topic, the physics of thermal radiation, that triggered one of the greatest revolutions in the history of science, the birth of quantum mechanics. In the late 19th century, physicists were very interested in understanding how hot objects radiate energy. They knew from experiments that the radiation emitted by a hot object depends on its temperature, and they could measure the spectrum, the distribution of energy across different wavelengths. For a perfect emitter, what physicists call a black body, this spectrum has a characteristic shape. It rises, peaks at a certain wavelength, and then falls off. The peak wavelength shifts towards shorter wavelengths as the temperature increases, which is described by Wien's displacement law. This is why a cool piece of iron glows dull red when you start to heat it, then orange, then yellow, then white, and if you could heat it enough, it would glow blue. The hotter the object, the shorter the wavelength of its peak emission, and the higher the frequency of the light it produces most intensely. This is directly observable in the cosmos. The Sun, with a surface temperature of about 5,500 degrees Celsius, emits most of its energy in the visible light range, peaking in the yellow-green part of the spectrum. This is not a coincidence. Our eyes evolved on this planet, bathed in sunlight, and they evolved to be most sensitive to the wavelengths that the sun produces most abundantly. We see the universe in sunlight colors because sunlight is what forged our vision. A cooler star like a red dwarf with a surface temperature of 3,000 degrees emits most of its energy in the infrared, with just a dim red visible glow. A hotter star, like a blue giant at 30,000 degrees, emits mostly in the ultraviolet, appearing a brilliant blue-white to our eyes. And your own body, at a temperature of about 37 degrees Celsius, or 310 Kelvin, emits radiation that peaks in the infrared at a wavelength of about 9 to 10 micrometers. This is why thermal cameras can see you in the dark. You are literally glowing with infrared light, visible to any detector sensitive to those wavelengths, even though your eyes cannot see it. Every warm thing is a beacon of infrared light, silently announcing its presence to the universe. Now, in the late 1800s, physicists tried to derive the spectrum of black body radiation from the known laws of classical physics, and they hit a wall. When they applied the classical theory of electromagnetism and thermodynamics, they got a formula that worked well for long wavelengths in the infrared, but predicted that the energy emitted at short wavelengths in the ultraviolet should increase without limit, rising toward infinity. This would mean that every warm object should emit infinite amounts of ultraviolet and X-ray radiation, which is obviously absurd. It would mean that every cup of coffee would fry you with gamma rays. This spectacular failure of classical physics was given the dramatic name the ultraviolet catastrophe, and it was a crisis in theoretical physics that left the greatest minds of the era baffled. Enter Max Planck, a German physicist who, in the year 1900, made a desperate and revolutionary move. To make the mathematics work, to derive a formula that matched the experimentally observed spectrum, Planck proposed that energy is not emitted or absorbed continuously, as everyone had always assumed. Instead, he said, energy comes in discrete packets, tiny indivisible chunks that he called quanta. The energy of each quantum is proportional to the frequency of the radiation, described by the now famous equation E equals h times f, where E is the energy of one quantum, is a new fundamental constant that we now call Planck's constant, and f is the frequency. This quantization of energy was a radical departure from everything physics had assumed for centuries. It was as if someone had said that water does not flow continuously, but comes in individual drops, each with a specific and indivisible volume. Planck himself was uneasy with his own idea. He reportedly spent years trying to find a way to derive his formula without quantization, but he could not. The mathematics demanded it, and slowly, other physicists began to realize that quantization was not just a mathematical trick, but a fundamental feature of reality. Einstein used it in 1905 to explain the photoelectric effect, proposing that light itself comes in quanta, in particles that we now call photons. Niels Bohr used it to explain the structure of atoms. Werner Heisenberg and Erwin Schrödinger and Max Born and Paul Dirac built on it to create quantum mechanics, the most successful and precise theory in the history of science. The theory that explains everything from the behavior of subatomic particles to the structure of NAR to the operation of the semiconductor chips in the device you are using to watch this video right now. And it all started with our topic. It all started with trying to understand how hot objects radiate energy. The question of how the sun's heat relates to the cold of space is not just a curiosity. It is the question that gave birth to quantum mechanics. It is the question that launched modern physics. Let me now share with you one of the most beautifully poetic facts in all of physics, and it connects directly to Wien's displacement law and the relationship between temperature and radiation. We said that the CMB, the afterglow of the Big Bang, currently has a temperature of 2.725 Kelvin and peaks in the microwave part of the spectrum. But when it was first emitted, 380,000 years after the Big Bang, it had a temperature of about 3,000 Kelvin and peaked in the visible light range. If you could have been there, the entire universe would have been glowing a warm orange-red, like the surface of a cool star, in every direction. Over the 13.8 billion years since then, the universe has expanded by a factor of about 1,080, and this expansion has stretched the wavelength of the CMB photons by the same factor, shifting them from visible light to microwaves and reducing their effective temperature from 3,000 Kelvin to 2.725 Kelvin. The universe is literally cooling down. The afterglow of creation is fading. And in the far distant future, as the universe continues to expand, the CMB will be stretched even further, its temperature dropping ever closer to absolute zero. And the night sky, already cold and dark, will become colder and darker still. This slow, inexorable cooling is a direct manifestation of the second law of thermodynamics playing out on the grandest possible stage. The universe began hot and ordered, with energy concentrated in a small space, and it has been spreading out, cooling down, and increasing in entropy ever since. The cold of space is not just a feature of the present, it is the direction of the future. It is the arrow of time written in temperature. Let us now turn our attention from the abstract physics to the very concrete and very human challenge of surviving in this environment. How do astronauts and their spacecraft deal with the extreme temperature paradox of space? The answer involves some of the most ingenious engineering ever devised by human minds, and it is a direct application of every principle we have discussed so far. Consider the International Space Station, that remarkable structure orbiting Earth at an altitude of about 400 kilometers, traveling at 27,600 kilometers per hour, completing one orbit every 90 minutes. Every 90 minutes, the ISS passes from the sunlit side of Earth to the shadow side and back again. When it is in sunlight, the sun-facing surfaces can reach temperatures of 121 degrees Celsius. When it passes into Earth's shadow, those same surfaces can plummet to negative 157 degrees Celsius. That is a temperature swing of nearly 280 degrees, happening every 45 minutes. How do the astronauts inside not alternately roast and freeze? How does the sensitive equipment not crack from thermal stress? How does the whole thing not tear itself apart? The answer is the active thermal control system, one of the most sophisticated thermal management systems ever built. Inside the station, water loops circulate through the modules, absorbing heat from electronics, from the crew's bodies, from sunlight entering through windows, and carrying it to the exterior of the station. But you cannot just dump heat into space through conduction or convection, because, as we discussed, those mechanisms do not work in a vacuum. Instead, the heat is transferred to an external ammonia loop, which carries it to massive radiator panels on the outside of the station. These radiators, which you can see in photographs of the ISS as large white panel structures, do not work by releasing hot air like a car radiator. They work by emitting infrared radiation. The hot ammonia flowing through the panels raises their temperature, and the panels radiate infrared photons into the void of space, slowly shedding their thermal energy into the cosmic cold. This is radiation at work, the only heat transfer mechanism available in the vacuum, being deliberately harnessed by human engineering to keep the station at a comfortable temperature. And here is something that surprises many people. The bigger thermal challenge on the ISS is not keeping warm, it is keeping cool. The station is packed with electronics, computers, experiments and other equipment that generates heat, plus 6 human bodies, each of which produces about 80 to 100 watts of thermal energy just by being alive. All of this heat is generated inside a sealed, insulated container floating in a vacuum where convection and conduction to the outside world are impossible. Without active cooling, the ISS would overheat in a matter of hours. The astronauts' biggest thermal enemy is not the cold of space, but the heat of their own bodies and machines, trapped inside with nowhere to go. The enormous radiator panels on the ISS are not there to keep the station warm. They are there to keep it from overheating. This is a direct and beautiful demonstration of our paradox. In the freezing void of space, the biggest problem is getting rid of excess heat. The spacesuits worn by astronauts during spacewalks, formerly called extravehicular mobility units or EMUs, face the same challenge in miniature. A spacesuit is essentially a tiny personal spacecraft, and it must maintain a comfortable temperature for the astronaut inside, despite the extreme temperature swings of the space environment. The spacesuit uses several layers of insulation, including multi-layer insulation similar to what covers the rest of the spacecraft, consisting of multiple layers of thin, reflective material like mylar or kapton, separated by spacers. These layers reflect solar radiation and reduce heat loss by radiation. Underneath the outer suit, the astronaut wears a liquid cooling and ventilation garment, essentially long underwear threaded with hundreds of feet of thin water-carrying tubes. This garment absorbs body heat through the circulating water and carries it to a sublimator, a device that exposes water to the vacuum of space, causing it to first freeze and then sublimate, turning directly from ice to water vapor. This phase change absorbs a tremendous amount of energy, the latent heat of sublimation, effectively carrying the astronaut's excess body heat away into space. The gloves and boots of the spacesuit have built-in heaters, because extremities are far from the body's core and tend to get cold, especially on the shadow side of the suit. And the visor of the spacesuit helmet is coated with a thin layer of gold, which reflects the harsh ultraviolet and infrared radiation of unfiltered sunlight, protecting the astronaut's face and eyes. That iconic gold visor is not decorative. It is a radiation shield, a direct application of the physics of electromagnetic radiation to keep the astronauts safe in the extreme thermal environment of space. During the Apollo missions to the Moon in the late 1960s and early 1970s, the spacecraft faced a particular version of the temperature paradox during the long coast between Earth and the Moon, a journey of about 3 days. During this coast, one side of the spacecraft faced the Sun and was heated to extreme temperatures, while the other side faced the void of space and cooled dramatically. If left in this orientation, the spacecraft would have developed a dangerous temperature differential, with one side expanding from heat while the other side contracted from cold, potentially cracking seals and damaging equipment. The solution was a maneuver charmingly called the barbecue roll, formerly known as passive thermal control. The spacecraft was set to slowly rotate around its long axis, about 3 revolutions per hour, like a rotisserie chicken, ensuring that all sides were evenly heated by the Sun and evenly cooled by space. This simple and elegant maneuver, rotating in the emptiness between worlds, was a beautiful practical solution to the temperature paradox, and it worked perfectly for every Apollo mission that used it. Perhaps the most spectacular modern example of engineering around the space temperature paradox is the James Webb Space Telescope, launched on Christmas Day 2021 and now operating at the second Lagrange point, about 1.5 million kilometers from Earth. The JWST is an infrared telescope designed to detect the faintest infrared light from the most distant galaxies, from the first stars that ever formed, from planets orbiting other stars. To do this, its instruments must be incredibly cold, because any warmth in the telescope itself would produce infrared radiation that would overwhelm the faint signals from space. The telescope's instruments operate at about 40 Kelvin, negative 233 degrees Celsius, and one instrument, the mid-infrared instrument called Mercury, must be cooled to just 7 Kelvin, negative 266 degrees Celsius, using an active cryocooler. How do you keep a telescope this cold when the Sun is constantly blasting it with radiation? The answer is the JWST sunshield, one of the most remarkable pieces of engineering ever created. The sunshield consists of 5 layers of a material called kapton, each layer thinner than a human hair and coated with reflective aluminum and silicon. These 5 layers, separated by vacuum gaps, work like a series of nested umbrellas. The first layer, facing the Sun, absorbs and reflects the bulk of the solar radiation. Some of the absorbed heat is re-radiated from the front surface back towards space. A small amount passes through to the second layer, which absorbs and re-radiates most of it, and so on, through all 5 layers, each one progressively cooler than the last. The result is astonishing. The sun-facing side of the sunshield can reach temperatures of about 85 degrees Celsius, hot enough to boil water. The instrument side, just a few meters away on the other side of those 5 thin layers, is at negative 233 degrees Celsius. A temperature difference of over 300 degrees across a distance you could cross in a few steps. This is the physics of radiation and vacuum made manifest in human engineering. The vacuum gaps between the sunshield layers are critical, because vacuum is the ultimate insulator. It prevents conduction and convection, forcing heat to move only by radiation, which the reflective surfaces are designed to minimize. The JWST literally exploits the very paradox we have been discussing. The cold of space is not a bug for the JWST, it is a feature. It is the reason the telescope can work at all. By hiding behind its sunshield, the JWST uses the natural cold of space to keep its instruments at the temperatures they need to peer back in time to the dawn of the universe. Let us now explore one of the most dramatic and often misunderstood questions related to our topic, and it is a question that I know many of you are asking right now. What would actually happen to a human body if it was suddenly exposed to the vacuum of space without a spacesuit? Hollywood has given us many dramatic and almost entirely wrong depictions of this. In some movies, the person instantly freezes solid, becoming a human ice sculpture in seconds. In others, the person explodes, their body bursting apart from internal pressure. In still others, the person's blood boils instantly, killing them in a spectacular and gory fashion. None of these is correct. The reality is more nuanced, more interesting, and in some ways even more terrifying than the movies suggest. If you were suddenly exposed to the vacuum of space, the first thing you would notice is that the air in your lungs would rush out. The vacuum outside your body would create an enormous pressure differential, and any air trapped in your lungs would expand rapidly and try to escape. If you tried to hold your breath, the expanding air could rupture your lungs, which could be fatal. So the first rule of accidental space exposure is do not hold your breath. Let the air go. After the air rushes out, you would lose consciousness in about 10 to 15 seconds due to oxygen deprivation. Your brain is the most oxygen-hungry organ in your body, and without oxygen-carrying blood reaching it, you would black out quickly. This is the primary danger. You would not feel pain. You would not explode. You would simply become lightheaded and then unconscious. During those 10 to 15 seconds of consciousness, you might notice some strange sensations. The water on your tongue and in your mouth would begin to boil. Not because it is hot, but because the boiling point of water depends on pressure, and in a vacuum, the boiling point drops below body temperature. Your saliva would bubble and evaporate from the surface of your tongue. The moisture in your eyes and on your skin would begin to evaporate as well. You might notice swelling as the water in your tissues begins to vaporize, causing your body to puff up slightly. This is called ebulism, and while it sounds dramatic, it is not immediately fatal. Your skin is strong enough to contain most of the swelling, and your blood would not boil because your circulatory system maintains its own internal pressure. Now here is the part that connects to our paradox. Would you freeze? And the answer is no, not quickly. In fact, the opposite. The main thermal concern in the immediate aftermath of space exposure is overheating, not freezing. This seems counterintuitive, but it follows directly from the physics we have discussed. On Earth, your body has three ways to lose excess heat: radiation, convection, and evaporation. Convection is the big one. The movement of air over your skin carries heat away constantly. Evaporation of sweat is the other major cooling mechanism. In space, there is no air for convection. That mechanism is gone. You are left with radiation and the brief evaporation of surface moisture. Your body, however, continues to generate heat through metabolism at the usual rate of about 80 to 100 watts. With your primary cooling mechanism gone, your body would actually start to warm up internally. Over time, as the surface moisture evaporates away and your body slowly radiates heat into the void, the surface of your skin would begin to cool. But this radiation cooling is slow, very slow, because radiation is the least efficient of the three heat transfer mechanisms for an object at human body temperature. It would take many minutes for your skin temperature to drop noticeably, and much longer than that for your core temperature to fall. The bottom line is that you would die of oxygen deprivation, not freezing, and it would happen in minutes, not seconds. If you were rescued within about 90 seconds and brought back to a pressurized environment, you would probably survive, although you might suffer some tissue damage from the swelling and the evaporation of moisture. After about 90 seconds, survival becomes unlikely, and after a few minutes, the lack of oxygen would cause irreversible brain damage and death. We actually have some real-world data on this, thanks to a terrifying accident at NASA in 1966. A technician named Jim LeBlanc was testing a spacesuit in a vacuum chamber when the pressurization hose to his suit disconnected, exposing him to a near vacuum. He remained conscious for about 14 seconds before blacking out. His last conscious memory was the sensation of the saliva boiling on his tongue. The chamber was repressurized within about 30 seconds, and LeBlanc regained consciousness and suffered no lasting ill effects. This incident, while frightening, provided valuable data confirming the theoretical predictions about human exposure to vacuum. You do not freeze. You do not explode. You lose consciousness quickly from lack of oxygen, and if rescued in time, you can survive. The slow radiation cooling of a body in space does eventually win out, of course. Given enough time, a human body floating in the void would slowly radiate its heat away, eventually approaching the ambient temperature of space, that 2.725 Kelvin of the CMB. But this process would take many hours, and even then, it would not look like the dramatic flash freezing of the movies. The body would cool slowly and unevenly, with the surface cooling first and the core retaining heat for a long time, similar to how a Thanksgiving turkey cools after being taken out of the oven. In the shadow of a planet or in deep space, away from any star's radiation, the body would eventually become incredibly cold. But in direct sunlight, the sun-facing side would be heated to above freezing temperatures, while the shadow side cooled dramatically, creating the same extreme temperature differential that we see on the Moon and on Mercury. Now, I want to take us into deeper waters. I want to go beyond the practical physics that we have been discussing and explore some of the more profound and mind-bending implications of the relationship between heat, radiation, vacuum, and temperature. These topics are at the very frontier of modern physics, and they connect our everyday paradox about the cold of space to the most fundamental questions about the nature of reality. Let us start with the sun's corona problem, because it contains a paradox within our paradox. We mentioned earlier that the sun's corona, the outermost layer of its atmosphere that is visible during solar eclipses as a beautiful pearly white halo, has a temperature of 1 to 3 million degrees Celsius. The surface of the sun, the photosphere, has a temperature of about 5,500 degrees Celsius. So the corona is hundreds of times hotter than the surface. This is deeply, deeply strange. Imagine standing next to a campfire. As you walk away from the fire, the temperature drops. You expect it to drop. More distance from the heat source means less heat. Now imagine that as you walk away from the campfire, the temperature actually increases. 10 feet away, it is 100 degrees. 20 feet away, it is 1,000 degrees. 50 feet away, it is 1,000,000 degrees. You would think you had lost your mind. And yet this is exactly what happens with the sun. The temperature increases as you move away from the surface and into the corona. This is called the coronal heating problem, and it has been one of the most persistent and important unsolved problems in solar physics for over 70 years, ever since the Swedish physicist Bengt Dedlund first measured the corona's temperature in 1942 by identifying highly ionized ion lines in the coronal spectrum. Several theories have been proposed to explain this mystery. One leading candidate is nanoflares, tiny magnetic explosions on the sun's surface that are too small to be individually detected, but that collectively could pump enormous amounts of energy into the corona. The idea is that the sun's tangled, complex magnetic field constantly creates tiny pockets of extreme magnetic stress, and when these pockets release their energy, they heat the surrounding gas to extreme temperatures. If millions of these nanoflares are going off continuously, they could explain the corona's extreme heat. Another theory involves Alfvén waves, a type of magnetohydrodynamic wave that travels along magnetic field lines. The idea is that these waves are generated by the turbulent convective motions on the sun's surface and propagate outward into the corona, carrying energy with them. When the waves dissipate, they dump their energy into the coronal gas, heating it. A third theory involves magnetic reconnection, a process in which magnetic field lines snap and reconfigure, releasing enormous amounts of stored magnetic energy as heat and kinetic energy. Magnetic reconnection is known to occur during solar flares, the sun's most powerful explosive events, and it may also occur on smaller scales continuously throughout the corona. NASA's Parker Solar Probe, launched in 2018, is attempting to solve this mystery by flying closer to the sun than any spacecraft in history. Named after the physicist Eugene Parker, who first proposed the existence of the solar wind in 1958, the probe is gradually reducing its orbit, using Venus gravity assists to pass through the sun's corona itself, directly sampling the environment and taking measurements in situ. The Parker Solar Probe carries a heat shield made of carbon composite foam that is just 4.5 inches thick, but can withstand temperatures of about 1,370 degrees Celsius, while keeping the instruments behind it at room temperature. This heat shield is a masterpiece of thermal engineering, exploiting the same physics of radiation and insulation that we have been discussing throughout this video. And the Parker Solar Probe has already returned groundbreaking data. It has found that the solar magnetic field near the Sun is much more structured and dynamic than expected, with sudden switchbacks and reversals that could be related to the coronal heating process. It has directly measured the solar wind being accelerated in ways that challenge existing models, and it has provided the first in situ observations from inside the corona, a region that until now could only be studied from a distance. The coronal heating problem is slowly being solved, and the solution will deepen our understanding of not just our Sun, but of stars throughout the universe. Now let us go even deeper and explore the connection between our topic and the very fabric of space-time itself. Albert Einstein's theories of relativity, both special and general, have profound implications for our understanding of temperature, radiation, and the vacuum of space. In special relativity, Einstein showed that the properties of the physical world depend on the relative motion of the observer. Time dilates, lengths contract. Energy and mass are interconvertible via E equals mc squared, and radiation behaves differently depending on your speed relative to its source. If you are moving toward a source of radiation, the radiation you receive is blue-shifted, its wavelength compressed, its frequency increased, and its perceived temperature raised. If you are moving away, the radiation is red-shifted, its wavelength stretched, its frequency decreased, and its perceived temperature lowered. This means that two observers moving at different speeds relative to the cosmic microwave background would measure slightly different temperatures for the CMB. In fact, we can measure this effect from Earth. As our solar system moves through space relative to the CMB rest frame, at a speed of about 370 kilometers per second, the CMB appears slightly warmer in the direction we are moving toward and slightly cooler in the direction we are moving away from. This is called the CMB dipole, and it is a direct, measurable consequence of special relativity applied to the background temperature of the universe. In general relativity, Einstein went further, showing that gravity warps space-time, bending the paths of light and affecting the flow of time. Near a massive object, time runs slower, light is redshifted as it climbs out of a gravitational well, and the vacuum itself is distorted. This gravitational redshift means that radiation emitted from a strong gravitational field loses energy as it escapes, appearing cooler to a distant observer. If you were near a black hole and emitted light, an observer far away would see that light as redder and cooler than you emitted it. Conversely, light falling into a gravitational well blue shifts and appears hotter. This creates a fascinating connection between gravity and temperature that is still being explored by theoretical physicists today. But perhaps the most mind-bending connection between vacuum, temperature, and fundamental physics comes from a phenomenon called the Unruh effect, predicted in 1976 by the physicist William Unruh. The Unruh effect states that an accelerating observer will perceive the vacuum of empty space as filled with thermal radiation, even though an inertial, non-accelerating observer in the same region of space sees nothing at all. The temperature of this radiation is proportional to the acceleration. The faster you accelerate, the hotter the vacuum appears to you. For an observer accelerating at 10 meters per second squared, roughly the acceleration due to gravity on Earth's surface, the Unruh temperature is incredibly tiny, about 4 times 10 to the negative 20 Kelvin, far too small to measure. But at extreme accelerations, like those near a black hole, the Unruh temperature can become significant. The Unruh effect blurs the boundary between something and nothing, between hot and cold, between full and empty. It tells us that the vacuum is not as empty as it seems, and that temperature at its deepest level is not just about moving particles, but about the very structure of space-time and the observer's relationship to it. The Unruh effect is closely related to one of the most famous predictions in theoretical physics, Hawking radiation, proposed by Stephen Hawking in 1974. Hawking showed that black holes are not truly black. They emit faint thermal radiation, a ghostly glow that slowly causes them to lose mass and eventually evaporate completely. This radiation arises from quantum effects near the event horizon, the boundary of a black hole beyond which nothing can escape. In simple terms, the intense gravitational field of the black hole creates particle-antiparticle pairs in the vacuum near the event horizon. Normally, these virtual particles would immediately annihilate each other and disappear, but at the event horizon, it is possible for one particle to fall into the black hole while the other escapes. The escaping particle carries energy away from the black hole, which means the black hole loses a tiny amount of mass with each escaping particle. Over unfathomably long periods of time, this process can cause the black hole to shrink and eventually evaporate entirely. The temperature of Hawking radiation depends on the mass of the black hole, and the relationship is inverse. The more massive the black hole, the cooler its Hawking radiation. A black hole with the mass of our Sun would have a Hawking temperature of about 60 billionths of a degree above absolute zero, far colder than the CMB, which means it is actually absorbing more radiation from the CMB than it is emitting. Such a black hole would not evaporate for an almost inconceivable period of time, roughly 10 to the 67th power years. But a tiny black hole with the mass of a mountain would have a temperature of billions of degrees and would be radiating ferociously, emitting gamma rays and other high-energy particles at a prodigious rate. And as a black hole evaporates and gets smaller, it gets hotter, and as it gets hotter, it evaporates faster, in a runaway process that ends in a final burst of radiation, an explosion of incredible intensity as the last remnants of the black hole vanish in a flash of energy. Hawking radiation connects quantum mechanics, general relativity, and thermodynamics in a way that no other phenomenon does, and it tells us something profound about our topic. Even in the most extreme gravitational environments in the universe, where space-time is warped beyond recognition and the very concept of space is stretched to its limits, the relationship between vacuum, temperature, and radiation persists. The cold of the vacuum is not just an incidental feature of our local environment, it is woven into the deepest fabric of physics. Let us now also talk about something even more fundamental. We have been discussing the vacuum of space as if it were truly empty, a perfect void containing nothing at all. But quantum mechanics tells us that the vacuum is far more interesting than that. According to quantum field theory, the most fundamental framework of modern particle physics, the vacuum is not empty. It is seething with activity. Quantum fluctuations, brief and random fluctuations in energy that arise from the Heisenberg uncertainty principle, constantly fill the vacuum with a fizzing, bubbling sea of virtual particles. These virtual particles pop into existence and vanish again in time spans so short that they cannot be directly observed, borrowing energy from the vacuum and returning it before anyone notices, like a quantum version of a bank error in your favor that gets corrected before the auditors arrive. These quantum fluctuations have real, measurable effects. The most famous is the Casimir effect, predicted by the Dutch physicist Hendrik Casimir in 1948 and experimentally confirmed many times since. If you place two metal plates very close together in a vacuum, the quantum fluctuations between the plates are restricted because only fluctuations with wavelengths that fit between the plates can exist there. Outside the plates, all wavelengths of fluctuation are possible. This creates an imbalance, with more quantum fluctuation pressure outside the plates than between them, resulting in a net force that pushes the plates together. This force is tiny but real, and has been measured with great precision. It is proof that the vacuum is not empty, that even perfect nothingness has structure and energy and properties. The energy of these quantum fluctuations, called zero-point energy or vacuum energy, is in principle enormous. Calculations of the total vacuum energy in a cubic meter of empty space, based on straightforward quantum field theory, yield a number that is staggeringly, absurdly large, roughly 10 to the 113th joules per cubic meter. This is more energy than exists in all the matter in the observable universe. Clearly something is wrong with this naive calculation, because if the vacuum really contained that much energy, its gravitational effect would have torn the universe apart long ago. This discrepancy between the predicted vacuum energy and the observed vacuum energy is known as the cosmological constant problem, and it is one of the greatest unsolved problems in all of physics. A mismatch of 120 orders of magnitude between theory and observation that has been called the worst prediction in the history of science. Interestingly, the vacuum does seem to have some energy. Observations of distant supernovae in 1998, which won the Nobel Prize for Saul Perlmutter, Brian Schmidt, and Adam Riess, showed that the expansion of the universe is accelerating. Something is pushing the universe apart, making galaxies fly away from each other faster and faster. This something has been given the name dark energy, and it constitutes about 68% of the total energy content of the universe. The leading hypothesis is that dark energy is a property of the vacuum itself, a form of vacuum energy, but at a level that is 120 orders of magnitude smaller than what quantum field theory naively predicts. Why the discrepancy? Nobody knows. It is one of the deepest mysteries in modern physics. But the point for our discussion is this: the vacuum of space, the cold, empty void that we have been discussing, is not truly empty or truly devoid of energy. It is filled with quantum fluctuations, it may contain dark energy, and it has properties that we are still struggling to understand. The vacuum is not nothing. It is something, and something quite mysterious at that. But here is the key connection back to our topic. None of this vacuum energy acts as heat in the way we normally understand it. The quantum fluctuations do not warm objects. The dark energy does not raise temperatures. These forms of energy exist in a fundamentally different way from thermal energy. They are part of the fabric of space-time itself, part of the ground state of the quantum fields, not the excited, jiggling motion of particles that we call temperature. So even though the vacuum of space is secretly full of exotic quantum energy, it is still effectively cold from a thermodynamic perspective. The vacuum may not be empty, but it is still cold. Now let me take you to a topic that I think brings the deepest meaning to our entire discussion, and that is the fate of the universe itself. We have been asking why space is cold while the sun is hot. We have answered this question in terms of heat transfer, radiation, vacuum physics, and thermodynamics. But there is a grander version of this question, and it is this: will the universe always have hot things and cold things? Will there always be stars burning furiously against the cold backdrop of space? Or is this merely a temporary phase, a brief and extraordinary era in the life of the cosmos, destined to end? The answer, according to our best understanding of thermodynamics and cosmology, is that this era is temporary. The universe is slowly, inexorably dying, and the mechanism of its death is the very same physics that makes space cold while the sun burns hot. The second law of thermodynamics states that in any closed system, entropy, a measure of disorder, of energy spread, of the number of possible arrangements of a system's components, always increases over time. Energy flows from hot to cold. Concentrated energy disperses. Ordered systems become disordered. This is not just a human observation or a rule of thumb. It is a fundamental law of nature, as inviolable as the law of gravity, and perhaps even more fundamental. The second law gives time its direction. It is the reason why cups of coffee cool down but never spontaneously heat up, why eggs break but do not unbreak, why we age and die and do not grow young. Time flows in the direction of increasing entropy, and this flow is as relentless and as universal as the expansion of space itself. Applied to the universe as a whole, the second law paints a picture of the far future that is almost unbearably desolate. Right now, we live in a universe where entropy is relatively low, where there are tremendous temperature differences, where the sun blazes at millions of degrees while space shivers at 2.7 Kelvin, where energy flows from hot to cold and in the process drives all the complexity and beauty and life that we observe. Stars burn. Planets orbit. Life evolves. Minds think. Civilizations rise. All of this is powered by the flow of energy from hot sources to cold sinks, by the very temperature difference that is the subject of this video. But this temperature difference is not permanent. The sun is burning through its hydrogen fuel, converting mass to energy at a rate of 4 million tons per second. In about 5 billion years, the sun will exhaust its hydrogen and begin to die, swelling into a red giant that will engulf Mercury, Venus, and possibly Earth, before shedding its outer layers and collapsing into a white dwarf, a dense stellar remnant that will slowly cool over billions of years, fading from white to yellow, to red to brown to black, eventually becoming a cold, dark cinder floating in the void. And the sun is not special. Every star in the universe faces the same fate, just on different timescales. The most massive stars burn out in just a few million years, exploding as supernovae and leaving behind neutron stars or black holes. Stars like our sun last about 10 billion years. The smallest, most miserly stars, red dwarfs that hoard their fuel with extreme efficiency, can last for trillions of years, but eventually they too will burn out. In roughly 10 to the 14th years, 100 trillion years from now, the last star in the universe will burn its last atom of hydrogen and go dark. The stelliferous era, the age of stars, the age in which we are privileged to live, will be over. After the last star dies, the universe enters the degenerate era, a long and dark period dominated by the remnants of stars, white dwarfs, neutron stars, and black holes. These objects will slowly cool, slowly lose energy through radiation, slowly approach the ever-dropping temperature of the expanding universe. Over inconceivably long periods, any remaining structures will decay. If protons are unstable, as some theories of particle physics suggest, then all ordinary matter will eventually decay into lighter particles, electrons, positrons, neutrinos, and photons. This process might take 10 to the 40th power years, a number so large that the entire age of the universe from the Big Bang to now is a rounding error by comparison. After proton decay, there would be no more atoms, no more molecules, no more solid matter of any kind, just a thin, cold soup of fundamental particles and radiation, dispersed across an ever-expanding void. But even this is not the end, because black holes remain. Black holes are the most durable objects in the universe. They do not decay through proton decay because they are not made of protons. They are made of warped space-time itself. But as Hawking showed, they do slowly evaporate through Hawking radiation, that faint quantum glow that we discussed earlier. A stellar mass black hole would take about 10 to the 67th years to evaporate. A supermassive black hole, like the one at the centre of our galaxy, with a mass of 4 million suns, would take about 10 to the 100th power years. 10 to the 100th. That is a 1 followed by 100 zeros. Write it out and it stretches across the page. Say it out loud and it takes a second. But live through it, and you would experience a span of time that makes the current age of the universe look like the blink of an eye within the blink of an eye within the blink of an eye. And yet, even this is not infinity. Eventually, the last black hole evaporates in a final burst of Hawking radiation, and the black hole era ends. What remains is the dark era, the final state of the universe. In this era, there is nothing left but a thin, cold, expanding gas of photons, neutrinos, electrons, and positrons, spread so thin across the expanding cosmos that particles virtually never encounter each other. The temperature of the universe, that CMB that is now 2.725 Kelvin, will have cooled to effectively zero. Not true absolute zero, because that is impossible, but so close that the difference is meaningless. There will be no stars, no planets, no life, no light, no warmth, no temperature differences, no energy gradients, no possibility of work or thought or change. Maximum entropy, perfect uniformity. Eternal, silent, dark, cold equilibrium. This is what physicists call the heat death of the universe, and despite the name, it is not death by heat, but death by the absence of heat differences. It is the ultimate triumph of the second law of thermodynamics, the final victory of entropy, the end of all temperature gradients, including the one between our sun and the cold of space. I want to sit with this for a moment, because I think it deserves reflection. Right now, in this instant, you and I exist in an incredibly special time. We exist in a universe that is still young, still full of temperature differences, still powered by the flow of energy from hot to cold. The sun burns. Space is cold. And in between, on a tiny rocky planet with a thin atmosphere and a magnetic field and liquid water, the flow of energy from hot sun through temperate earth into cold space drives every process that sustains life. Photosynthesis captures the sun's radiation and converts it into chemical energy. Weather patterns distribute heat around the globe, ocean currents circulate warmth from the equator to the poles, ecosystems process energy from producers to consumers to decomposers. Your own body is a heat engine, burning food, generating warmth, radiating it into the environment, a tiny eddy in the vast river of energy flowing from the sun into the void. Every heartbeat you have ever had has been powered by this flow. Every thought you have ever had has been a ripple in this current. Every civilization humanity has ever built has been a temporary, beautiful, improbable structure maintained by the ceaseless river of energy from our star into the dark. And all of it, every bit of it, exists because of the paradox we have been exploring. The sun is hot, space is cold, energy flows from one to the other, and in the sweet spot between them, on a world neither too hot nor too cold, life found a way. If the vacuum of space were warm, if it somehow absorbed and retained the sun's heat, then there would be no temperature gradient, no energy flow, no driving force for any of the processes we call life. If the sun were cold, if it did not burn, there would be no energy source to begin with. It is the combination of a blazing star and a freezing void, of a nuclear furnace and an infinite cold sink, that creates the conditions for everything we know and love and are. We are creatures of the temperature difference. We are born from the paradox. And when the paradox finally resolves, when the last star burns out and the last temperature gradient vanishes, we will go with it. But that is not today. Today the sun still burns. Today space is still cold. Today the energy still flows. And today, right now, you are here, reading these words, thinking these thoughts, your brain consuming 20 watts of power derived ultimately from the nuclear fusion of hydrogen in a star 93 million miles away, carried to you as radiation through a vacuum so cold that it is almost at absolute zero, absorbed by the chlorophyll in plants or the phytoplankton in the ocean, converted to chemical energy, passed up the food chain, consumed by you, metabolized in your cells, and used to fire the neurons that are processing this sentence. You are a child of the sun and the void. You are the universe's way of contemplating its own temperature. Let us now talk about some of the more specific and remarkable aspects of this topic that I want to make sure we cover, because there are details here that I think will surprise and delight you. Let us talk about what happens to different materials in the space environment, because the way different substances respond to the extremes of space tells us a lot about the physics of radiation and thermal equilibrium. Consider a simple metal sphere floating in space at Earth's distance from the sun. If this sphere is made of a dark, highly absorptive material, it will absorb a large fraction of the incoming solar radiation and reach a relatively high equilibrium temperature. A perfect black body sphere at this distance would reach about 279 Kelvin, as we calculated earlier. But what if the sphere is made of a highly reflective material, like polished aluminum or silver? Such a sphere would reflect most of the incoming sunlight, absorbing very little, and its equilibrium temperature would be much lower. A perfectly reflective sphere, which is a theoretical impossibility but useful for illustration, would absorb no solar radiation at all, and would cool to the CMB temperature of 2.725 Kelvin. In practice, no real material is perfectly reflective, but materials with high reflectivity, like the silvered thermal blankets on spacecraft, come close enough to dramatically reduce solar heating. This is why spacecraft are covered in multi-layer insulation that appears silvery or golden. The reflective surfaces reject most incoming solar radiation, preventing the spacecraft from overheating on the sun-facing side. Now consider the same metal sphere in shadow, shielded from the sun by a planet or some other large body. With no direct solar radiation to absorb, the sphere's temperature is determined by the balance between any residual radiation sources: R light, CMB, reflected light from nearby objects, and its own thermal emission. In deep shadow far from any significant radiation source, the sphere would slowly cool toward the CMB temperature. But slowly is the operative word. Radiation is an inefficient cooling mechanism for an object at low temperatures, because the Stefan-Boltzmann law tells us that the power radiated is proportional to T to the fourth. As the temperature drops, the radiation rate plummets. A sphere at 300 Kelvin radiates much more energy than the same sphere at 100 Kelvin, which radiates much more than the same sphere at 10 Kelvin. The cooling curve is not linear, but exponential, getting ever slower as the temperature approaches the background temperature. This is why objects in shadow do not instantly freeze. They cool rapidly at first, then slower and slower, asymptotically approaching, but never quite reaching the background temperature. This has practical implications for spacecraft design. When a spacecraft passes into the shadow of a planet, it does not instantly lose all its heat. It cools gradually, and engineers can predict this cooling curve with great precision using the Stefan-Boltzmann law and the known thermal properties of the spacecraft materials. The ISS, for example, passes into Earth's shadow for about 36 minutes of each 90-minute orbit, and its external temperature drops significantly during these shadow passes. But the internal temperature barely changes because the insulation and thermal control systems are designed to handle exactly this cycling. Let me also talk about something that many people find counterintuitive, and that is the color of objects in space. On Earth, we are accustomed to judging temperature by color. Hot coals are red. Blue flames are hotter than red flames. White hot is hotter than red hot. We associate color with temperature intuitively. But in space, the visual color of an object tells you almost nothing about its temperature. A white-painted spacecraft and a black-painted spacecraft at the same distance from the sun will have very different equilibrium temperatures, but neither one's visual color tells you its temperature directly. The white spacecraft, being more reflective in the visible spectrum, absorbs less solar radiation and stays cooler. The black spacecraft absorbs more and gets hotter. But here is the twist. The color that matters for thermal equilibrium is not just the visible color. It is the absorptivity and emissivity across the entire electromagnetic spectrum, including the infrared, which is invisible to our eyes. An object can appear white to your eyes, but be a strong absorber and emitter in the infrared, or vice versa. Engineers designing spacecraft thermal coatings care about the ratio of solar absorptivity to infrared emissivity, often denoted alpha over epsilon, because this ratio determines the equilibrium temperature. A material with low alpha reflects most epsilon, and high epsilon efficiently emits infrarain, will stay very cool in space, even in direct sunlight. A material with high alpha and low epsilon does not radiate infrared well, will get very hot. Spacecraft thermal engineers spend enormous efforts selecting and designing coatings with just the right alpha over epsilon ratio for each surface, tweaking the spacecraft's temperature to be exactly where they need it. This brings us to another fascinating topic: thermal coatings and the engineering of spacecraft surfaces. The gold-coloured foil that you see on many spacecraft, which gives them that distinctive shiny appearance, is not gold. It is usually Kapton or mylar film, coated with a thin layer of aluminum or occasionally actual gold. These multi-layer insulation blankets, or MLI, consist of multiple layers of reflective film separated by spacers, usually made of netting or other low-conductivity materials. Each layer reflects a portion of the incoming radiation, and the vacuum gaps between layers prevent conduction, creating an extremely effective thermal barrier. A typical MLI blanket might have 10 to 30 layers and can reduce heat loss by radiation by a factor of 10 to 100 or more compared to an uninsulated surface. The MLI blankets on the James Webb Space Telescope sunshield, as we discussed, are a particularly spectacular example of this technology, but even much simpler spacecraft use MLI extensively. Almost every satellite in orbit has at least some MLI covering. Some spacecraft also use optical solar reflectors, which are essentially very good mirrors that reflect sunlight while efficiently emitting infrared radiation. These are used on surfaces where the goal is to stay as cool as possible while still being able to dump internally generated heat. Other surfaces might use dark, high emissivity coatings to maximize radiative heat loss, like the black radiator panels on the ISS. The choice of surface coating is a critical engineering decision that can mean the difference between a spacecraft operating within its temperature limits and overheating or freezing. I want to also talk about a phenomenon called cold welding, because it is a direct and sometimes troublesome consequence of the vacuum of space, and it connects to our understanding of how the vacuum affects materials in ways that go beyond just temperature. On Earth, metal surfaces are always covered with a thin layer of oxide and contaminants, moisture, organic molecules, dust, and other substances that stick to the surface from the atmosphere. These layers prevent direct contact between the bare metal atoms of different objects. But in the vacuum of space, these surface layers can slowly evaporate or be removed by ultraviolet radiation, exposing the bare metal underneath. When two bare metal surfaces come into contact in a vacuum, their atoms can bond directly to each other, forming a single piece of metal without any heating or welding process. This is called cold welding, and it was a serious concern during the early days of space exploration. Engineers worried that mechanisms with metal-to-metal contacts might cold weld together and become permanently stuck. In practice, cold welding in space is less common than initially feared, because most spacecraft surfaces retain enough oxide layers and contamination to prevent it, and surface treatments like anodizing or applying lubricants further reduce the risk. But it remains a consideration in spacecraft design, particularly for mechanisms that must operate over long periods in the vacuum. Now let me talk about another aspect of our topic that I find absolutely mesmerizing, and that is the question of shadows in space. On Earth, shadows are not completely dark. Even in shadow you can see, because light scatters off the atmosphere, off dust particles, off walls and other surfaces, filling in the shadow with diffused light. Stand in the shade of a tree on a sunny day, and you can still see perfectly well. The shadow is cooler than the sunlit area, but it is not dramatically different, maybe 10 or 20 degrees at most. But in space, without an atmosphere to scatter light, shadows are absolute. Step behind a rock on the moon, and the shadow is pitch black. No light reaches the ground in shadow, because there is no atmosphere to scatter the sunlight around the obstacle. You literally cannot see anything in the shadow without artificial light. And the temperature drops dramatically. In direct sunlight on the moon, the surface might be 127 degrees Celsius. In the shadow, just a step away, it could be negative 173 degrees Celsius. This 300-degree temperature drop happens across a boundary that might be just inches wide. There is no gradual transition, no shade in the way we experience it on Earth. There is sunlight, and there is shadow, and the two are as different as fire and ice. This extreme shadow effect has real implications for lunar exploration. Astronauts walking on the moon during the Apollo missions experienced dramatic temperature differences on their spacesuits as they moved between sunlit and shadowed areas. The permanently shadowed craters at the moon's poles, which never receive direct sunlight due to the angle of the sun and the depth of the craters, are among the coldest places in the entire solar system. Temperatures in these permanently shadowed regions can drop to negative 240 degrees Celsius, colder than the surface of Pluto. And these ultra-cold craters are scientifically fascinating because they may contain deposits of water ice that have been trapped there for billions of years, delivered by comet impacts and preserved by the eternal cold. The Alcross mission in 2009 deliberately crashed a rocket stage into one of these shadowed craters and detected water vapor in the resulting plume, confirming that water ice exists on the moon. Future lunar explorers may mine this water ice for drinking, for growing crops, and most importantly, for splitting into hydrogen and oxygen to use as rocket fuel. The extreme cold of lunar shadows, a direct consequence of the vacuum of space and the physics of radiation, might be the key resource that enables humanity to establish a permanent presence on the moon. Let me also discuss the fascinating phenomenon of how sound, or more precisely the complete absence of sound, relates to the vacuum of space and our temperature paradox. Sound is a pressure wave that travels through a medium, air, water, solid material. It requires particles to propagate, because sound is literally a wave of compression and rarefaction passing through matter. In the vacuum of space, with virtually no particles, sound cannot travel. Space is silent. Absolutely, utterly, profoundly silent. This is not just an inconvenience, it is a consequence of the same fundamental reality that makes space cold. The absence of matter that prevents conduction and convection also prevents the propagation of sound. The vacuum is cold because there are no particles to carry heat. The vacuum is silent because there are no particles to carry sound. Both phenomena spring from the same root cause, the emptiness of the void. But I should note that this silence is not absolute everywhere. In the tenuous gas clouds between stars, the interstellar medium, there are enough particles to support very low-frequency sound waves, although the wavelengths of these waves are so enormous, measured in light years, that they bear no resemblance to anything we would recognize as sound. In 2003, astronomers detected sound waves in the hot gas surrounding the Perseus galaxy cluster. With a frequency of about one cycle every 10 million years, a B-flat, 57 octaves below middle C. These are pressure waves propagating through the hot intracluster medium, and they carry enormous amounts of energy, potentially contributing to the heating of galaxy cluster gas and preventing it from cooling and forming stars. So even in the almost empty reaches between galaxies, the physics of pressure waves, temperature, and heat transfer are at work on scales that dwarf anything in our solar system. Let us now explore an aspect of our topic that brings together everything we have discussed and connects it to the most fundamental question of all, the arrow of time and the nature of entropy. We have mentioned the second law of thermodynamics several times, and we have said that entropy always increases, that energy flows from hot to cold, and that this is the direction of time. But I want to dive deeper into what this really means, because it is the philosophical heart of our paradox. Consider the sun and the cold of space. The sun is a region of concentrated energy, a hotspot in a cold universe. Energy flows from the sun into the cold of space, and this flow powers everything we know. But why does energy flow from hot to cold and not the other way around? The second law says it just does. But why? Is it a fundamental law of physics, like the conservation of energy? Or is it something else? Something more subtle? The answer, surprisingly, has to do with probability. The second law of thermodynamics is not actually a law in the same sense as Newton's laws, or the law of conservation of energy. It is a statistical statement. It says that energy flows from hot to cold because there are enormously more ways for energy to be spread out than there are for it to be concentrated. Imagine a room with two halves separated by a wall. You put all the air molecules on one side and remove the wall. What happens? The molecules spread out to fill both halves. Not because there is a force pushing them, but because there are vastly more ways for the molecules to be spread across both halves than there are ways for them to be concentrated in just one half. The probability of all the molecules ending up back on one side, spontaneously, is not zero. It is just unimaginably small. For a room with a realistic number of molecules, the probability is so small that if you waited for the entire age of the universe, trillions of times over, it would still be essentially guaranteed to never happen. The second law says that entropy increases because the universe is overwhelmingly more likely to move towards states of higher entropy than towards states of lower entropy. It is not impossible for entropy to decrease. It is just so improbable that it effectively never happens for macroscopic systems. This probabilistic nature of the second law has a profound implication for our topic. The sun is hot and space is cold because the universe started in a state of very low entropy, a very unlikely state. The Big Bang created a universe that was remarkably uniform, with energy concentrated in specific ways that permitted the formation of stars and galaxies. Why the universe started in this low entropy state is one of the deepest unsolved problems in cosmology. Roger Penrose, the Nobel Prize-winning physicist, has called it the most important unexplained fact about the universe. Whatever the reason, the low entropy of the Big Bang is the ultimate source of all the temperature differences we observe today, including the one between our sun and the void of space. The sun is hot because gravity pulled hydrogen together and ignited nuclear fusion, a process that converts gravitational potential energy, a warm of low entropy, into thermal energy, a warm of higher entropy. The cold of space is the cold reservoir toward which this energy flows as entropy increases. And life, our life, is the beautiful, complex temporary pattern that forms in between, like an eddy in a river, sustained by the flow of energy from low entropy to high entropy, from hot to cold, from sun to void. This perspective reveals something remarkable about the paradox we have been exploring. The question, why is space cold when the sun is hot, is ultimately equivalent to the question, why does the universe have low entropy? And that question is equivalent to, why did the Big Bang happen the way it did? And that question connects to the most fundamental mysteries about the origin and nature of existence itself. Our simple question about temperature has led us, step by step, to the deepest questions in physics and philosophy. And this is the beauty of science. Every question, pursued far enough, opens onto the infinite. Let me now circle back and discuss some additional fascinating details about the thermal environment of space that I think add richness and depth to our understanding. One topic that deserves attention is the phenomenon of outgassing, which is the release of gases trapped in materials when they are exposed to the vacuum of space. On Earth, many materials, plastics, adhesives, paints, and other compounds, contain volatile substances that are held in the material by atmospheric pressure. When these materials are placed in the vacuum of space, these trapped gases escape, sometimes dramatically. Outgassing is a significant concern for spacecraft because the released gases can contaminate sensitive optical surfaces, interfere with scientific instruments, and degrade thermal coatings. Materials used in spacecraft construction must be tested for outgassing and selected to minimize this effect. This is another way in which the vacuum of space creates engineering challenges that are unique and not encountered in any terrestrial environment. Another fascinating detail is the phenomenon of thermal cycling fatigue. As we discussed, objects in orbit around a planet experience repeated temperature swings as they move in and out of sunlight. These temperature swings cause materials to expand and contract repeatedly, and over hundreds or thousands of cycles, this repeated expansion and contraction can cause materials to crack, delaminate, or otherwise fail through fatigue. The ISS has experienced over 150,000 thermal cycles since it was first launched. with each cycle subjecting its materials to temperature swings of up to 270 degrees Celsius. The fact that the station's structure has held up as well as it has is a testament to the engineering of its materials and joints, which were designed to accommodate these extreme thermal loads. I also want to talk about the thermal environment of deep space, far from any star. In the vast reaches between stars, in the interstellar medium, conditions are extreme in a different way than what we find near our Sun. The interstellar medium is not uniform. It consists of a complex mixture of hot, warm and cold gas and dust, organized into structures by gravity, radiation, magnetic fields, and supernova explosions. Some regions, like the hot ionized medium created by supernova blast waves, can have temperatures of millions of degrees, though as we discussed, the density is so low that this temperature represents very little actual thermal energy. Other regions, like cold molecular clouds, where new stars are forming, can have temperatures as low as 10 Kelvin, just a few degrees above the CMB. These molecular clouds are the densest parts of the interstellar medium, with hundreds to thousands of molecules per cubic centimeter, which is still an incredibly good vacuum by terrestrial standards, but is dense enough for the gas to absorb and emit radiation and to maintain a well-defined temperature. It is in these cold, dark clouds that new stars are born, as gravity slowly pulls the densest regions together until the pressure and temperature at the center become high enough to ignite nuclear fusion, and a new star blazes to life, pumping energy into the cold void, recreating the temperature difference that is the subject of this video. The cycle of stellar birth and death is one of the most profound aspects of our topic. Stars are born in cold clouds, they burn hot for millions or billions of years, they pump energy into the cold of space, and when they die, they return much of their material to the interstellar medium, enriched with heavier elements forged in their nuclear fires. These enriched materials become part of new molecular clouds, which collapse to form new stars and planets, and the cycle repeats. Our own Sun and solar system formed from such a cloud about 4.6 billion years ago, and the atoms in your body, the carbon, oxygen, nitrogen, calcium, iron, and all the other elements that make up your flesh and bones and brain, were forged in the nuclear furnaces of stars that lived and died long before our Sun was born. You are literally made of stardust, of atoms that were once in the cores of ancient stars, where temperatures reached millions of degrees before being blasted into the cold of space by supernova explosions, cooling over millions of years in the dark between stars, eventually being swept up into a new cloud, collapsing into a new star system, coalescing into a planet, and through billions of years of chemistry and biology, becoming you. The temperature paradox we have been discussing is not just an abstract fact about physics. It is the story of your own origin, written in the language of heat and cold, radiation and vacuum, entropy and time. Let us also spend some time discussing an often overlooked but critically important aspect of Earth's thermal balance, and that is the role of Earth's magnetic field. Earth has a strong magnetic field generated by the motion of liquid iron in its outer core, a process called the geodynamo. This magnetic field extends far into space, creating a region called the magnetosphere that deflects most of the charged particles streaming from the Sun in the solar wind. Without the magnetic field, the solar wind, a constant flow of protons and electrons moving at speeds of 300 to 800 kilometers per second, would directly impact Earth's atmosphere. Over time, this would strip away the atmosphere, as has happened on Mars, which has only a very weak residual magnetic field, and consequently an atmosphere that is only 1% as thick as Earth's. The loss of Mars's atmosphere is directly related to the loss of its magnetic field, which is thought to have occurred about 4 billion years ago, when Mars's core cooled and solidified, shutting down the geodynamo. Earth's magnetic field also protects us from cosmic rays, high-energy particles from outside the solar system that can damage DNA and pose a serious radiation hazard. Inside the magnetosphere, we are shielded from most of these particles. But the magnetosphere is not a solid barrier. It is distorted by the solar wind. Compressed on the sun-facing side and stretched into a long tail on the opposite side, and during solar storms when the sun emits bursts of especially energetic particles, the magnetosphere can be breached, allowing particles to reach the upper atmosphere and causing phenomena like the aurora borealis and aurora australis, the northern and southern lights. These beautiful displays of coloured light are actually a visible manifestation of our temperature paradox. The sun's energy, in the form of charged particles, is interacting with Earth's magnetic field and atmosphere, heating the upper atmosphere and causing gas molecules to glow. It is the sun's radiation energy being converted to visible light right before our eyes, a nightly reminder of the violent, energetic relationship between our hot star and our planet's fragile shield. The connection between the magnetic field and the thermal environment of a planet is even more profound when we consider Venus. Venus is similar in size and composition to Earth, but it has virtually no magnetic field. This has contributed to the loss of hydrogen from its upper atmosphere over billions of years, which in turn has contributed to the loss of water from Venus's surface. Without water, the carbon cycle that regulates CO2 on Earth could not operate on Venus, leading to the buildup of CO2 in the atmosphere and the runaway greenhouse effect that makes Venus the hottest planet in the solar system. So the absence of a magnetic field did not just expose Venus to the solar wind. It set in motion a chain of events that fundamentally altered the planet's thermal environment, turning a world that might once have been habitable into the hellscape it is today. The magnetic field, the atmosphere, the greenhouse effect, the surface temperature, these are all connected in a complex web of cause and effect, and the sun's radiation and the cold of space are the driving forces behind all of it. I want to now take a moment to discuss something that you might call the philosophy of the paradox, because I think there is a lesson in our exploration that goes beyond the physics. When we first encountered the paradox, when we first asked why space is cold when the sun is hot, it seemed like a genuine contradiction. It seemed like there was something fundamentally inconsistent about a blazing star coexisting with a freezing void. But as we have explored the physics, we have found that there is no contradiction at all. The sun being hot and space being cold are not in tension with each other. They are complementary aspects of a single, coherent physical picture. The sun is hot because nuclear fusion generates enormous energy. Space is cold because there is no matter in the vacuum to absorb and retain that energy. The energy travels through the void without interacting with it, and only heats the matter it eventually strikes. It all makes perfect sense once you understand the key concepts of temperature, heat transfer, and radiation. And I think there is a broader lesson here about how we encounter paradoxes in life and in science. Very often, what appears to be a paradox is actually a gap in our understanding. The contradiction is not in nature, it is in our model of nature. When we fill the gap, when we learn the missing concept, the paradox dissolves, and what remains is a deeper, richer, more beautiful understanding of reality. The apparent paradox of cold space and a hot sun dissolves when we understand what temperature really is and how heat really transfers, and in its place, we get a magnificent tapestry of physics that connects the quantum mechanics of photon emission to the thermodynamics of stellar evolution to the engineering of space exploration to the fate of the universe. The paradox was not an obstacle, it was a doorway, and by walking through it, we have discovered far more than we ever expected. Let me also address a question that many scientifically curious minds will be asking at this point. We have said that radiation is the only way to transfer heat in a vacuum, but is that really true? Are there any other mechanisms at all? The answer is that in the classical macroscopic world, yes, radiation is the only mechanism, but at the quantum level, there are some intriguing possibilities. We already mentioned the Casimir effect, which creates a force between closely spaced surfaces due to quantum vacuum fluctuations. There is also a quantum thermal effect called near-field radiative heat transfer, which can exceed the classical Stefan-Boltzmann limit when two surfaces are brought closer together than the thermal wavelength of their emission. typically on the order of 10 micrometers. At such close distances, quantum tunneling of photons and coupling of evanescent electromagnetic waves can transfer heat at rates much higher than classical radiation theory predicts. This effect has been measured experimentally and is an active area of research with potential applications in nanotechnology and energy harvesting. But these quantum effects operate at very small scales and do not significantly affect the macroscopic thermal environment of space. In the vast distances between planets and stars, classical radiation is effectively the only game in town. There is another mechanism that is sometimes confused with heat transfer in space, and that is particle radiation. The flow of charged particles like protons, electrons, and heavier ions from the sun These particles carry kinetic energy, and when they strike a surface they deposit that energy as heat, but this is not a separate mechanism of heat transfer. It is simply a form of energy transfer via matter, similar to conduction at a microscopic level, where fast-moving particles transfer energy to slower-moving particles through collisions. The solar wind does carry a significant amount of energy, about 1% as much as solar electromagnetic radiation, and it does heat the objects it strikes, but it is a minor contributor to the thermal environment of space compared to electromagnetic radiation from the sun. Let me now discuss one more topic that I think perfectly illustrates the beauty and elegance of the physics we have been exploring, and that is the concept of thermal radiation as a form of light. When we think of light, we usually think of the visible light that our eyes can see, the rainbow of colours from red to violet. But visible light is just a tiny sliver of the electromagnetic spectrum, which stretches from radio waves with wavelengths of kilometers to gamma rays with wavelengths smaller than atomic nuclei. All of these are fundamentally the same thing: electromagnetic waves propagating disturbances in the electromagnetic field, photons of various energies, and all of them can be produced by thermal radiation by objects with different temperatures. The connection between temperature and the kind of light an object emits is one of the most elegant relationships in physics. A room temperature object at about 300 Kelvin emits infrared light with a peak wavelength of about 10 micrometers, far beyond what your eyes can see. An incandescent light bulb filament at about 3000 Kelvin emits a broad spectrum that peaks in the infrared but extends into the visible range, which is why you can see the warm glow of an incandescent bulb. The sun, at 5500 Kelvin, peaks in the visible range, in the yellow-green part of the spectrum, which is why sunlight looks white to us. It is a mixture of all visible colours with a slight emphasis on yellow-green. A very hot star, at 30,000 Kelvin or more, peaks in the ultraviolet and appears blue-white, because the tail of its emission spectrum extending into the visible range is strongest at the blue end. And a room temperature object, or a human body, or the surface of a planet at night, all emit infrared light, invisible to our eyes but detectable by infrared cameras and sensors. This means that every object in the universe is constantly glowing with light, announcing its temperature to any detector sensitive enough to measure it. You are glowing right now. Your body is emitting about 100 watts of infrared radiation, silently, invisibly, in every direction. If you could see an infrared, every person would be a glowing beacon, every warm object would shine, and the world would look utterly different. The night would not be dark, because every warm surface, every building, every car, every animal would be emitting infrared light. In fact, this is exactly what infrared cameras show us. They make the invisible thermal glow of objects visible, translating temperature into colour, and the images are hauntingly beautiful. And here is the connection to our paradox. The radiation that objects emit to cool down in space is this same thermal glow. When the IS radiator panels emit infrared radiation to dump excess heat into the void, they are literally glowing in the infrared, like giant infrared flashlights pointed at the cosmos. When your body radiates heat in the vacuum of space, It is emitting infrared photons that sail away into the darkness at the speed of light, never to return, carrying tiny packets of your thermal energy into the infinite cold. Heat transfer by radiation is heat transfer by light, and the cold of space is maintained because this light passes through the vacuum without being absorbed, just as visible sunlight passes through the vacuum on its way from the sun to your eyes. The vacuum is transparent to all electromagnetic radiation, from radio to gamma, and this transparency is the fundamental reason why it does not warm up. Light passes through, energy passes through, but the void itself remains untouched, unchanged, indifferent